All right, we're going to look at exponential and logarithmic functions and their transformations. And the transformations, is going to be very similar to what we did before with our horizontal and vertical shifts and our reflections and things like that. So this is from page 63 to 64 of your handbook. So the two functions that we're going to look at, they're still exponential and logarithmic, but they're using a number that might not be familiar to you. So when we look at e, that is actually equal to about 2.7. And so on your calculator, if you want to see where that number is coming from, you might see a button that has ln on it. And then right above that button, you're going to see something like e to the x power. And so if you want to use the little button that is actually like above the button, you're going to have to push shift first, or sometimes you'll see a second button. And then when you hit ln, it will prompt you to put e to the x. And so if you want to know the value of e, we're really looking at e to the first power. So when you punch that into your calculator, you'll see that 2.7. Now, e is an irrational number, just like pi. So like when you think about the number pi, you might think, oh, well, that's just 3.14. Well, it's approximately 3.14. It is irrational, just like e is. But again, when you see e, it would be great if you could start thinking about that as, oh, that's about 2.7. And so if we're asked to graph y equals e to the x, this is really just looking at what we saw previously, which is y equals like 3 to the x, or well, somewhere between y equals 3 to the x and y equals 2 to the x. It's just the natural exponential function. And so when you think about what the graph would look like, it'll look just like our 3 to the x and 2 to the x. It'll be of that form. So let's punch in some values here. We'll plug in a 1, a 0, -1. There's a couple more spaces, but I think we'll get an idea after plugging in these. So we already know that e to the first power is about 2.7. E to the 0 power, well, that's always equal to 1, any number to the 0 power, which remember that matches up with our 0.01, which is on every exponential function, including the natural exponential function. E to the -1, that's just 1 over e, so it's 1 over about 2.7, which when we divide 1 divided by 2.7, we get about 0.37. So if we sketch just those values, let's see what's going on here. We'll put a 1 here up at just under 3. 0, 1 is on there, and then at -1, we're at 0.3. So this should look familiar if we start connecting those dots. This is going to keep growing and growing and growing. It's increasing while this is going to get closer and closer and closer to the x-axis, still never touching it. And that will also have a horizontal asymptote on the x-axis, because again, none of these values will ever go negative. You're looking at plugging in exponents that are both positive and negative, but they only end up with outputs that are positive. So our asymptote will be the line y equals 0. Our domain will be from -infinity to infinity, and our range will be 0 to infinity. Next, we're going to look at the inverse of our natural exponential function, and that is the natural log function. So we see this ln x. This is really log with the base of that e number. And that ln that you're seeing, it's like log natural, or natural log is how we read that. And so since it's the inverse of e to the x, we know we can just interchange the values from up above. So we know, if we kind of scooch down here, that when you plug in 2.7, that should pop out a 1. When you plug in a 1, you should get 0. Again, that's that number that will happen on every log function. And when you plug in 0.37, you get about -1. And this matches up with the notation as well, so kind of following from just looking at the function. If you look at natural log of, remember we were using this number as about e, so natural log of e, that's saying log base e of e. So e to what power, that's really the question, will make an e? Well, that has to be a 1. So when we plug in an e to our function, we know that that's going to output a 1. Similarly, if we're looking at the next one down here, we have natural log of 1. That's just looking at log with the base e of 1. So remember that's saying e to what power makes 1. That would have to be a 0. So you input 1, output 0. So let's look at what the graph of this is going to look like. Remember, it's the inverse. So if we're looking up at the previous graph we made, it's going to reflect over that line y equals x. So let's plot these points and see that happen. So at about 2.7, we're up at 1. At 1, we're at 0. And at 0.37, we're at -1. So if we connect those dots, we can see that's happening. Now, as your x values get bigger and bigger and bigger, our y values are also going to be growing, but they're not growing too fast. And when we plug in x values that get closer and closer to 0, that's taking us more and more negative, because remember, the log function is really getting us the exponents that end up with these results. So if we're a really tiny number, that means we're going to be a very high negative exponent. And so this is the graph of natural log of x, which I think is what you would expect. And it will have now a vertical asymptote through the y-axis, and we'll have x equals 0 for that. Our domain is going to be from 0 to infinity, again, not including 0, and our range will be from -infinity to infinity. Okay, when we flip the page, we're looking at graphing a whole bunch of exponential and logarithmic functions that have been transformed. So we've already seen a lot of the transformations with our basic functions from the beginning of our class, but now we're going to do it with these new log and exponential functions. So actually what I want to try first is just going through each of these functions and giving you a chance to describe the transformations that you see, keeping in mind that we're talking about exponential functions being the parent graphs and also log functions being the parent graphs. So I'll give you a minute to try and write down the transformations that you think you see happening. So when we look at the first equation here, we can see that the +1 is inside the exponent with the x, so that's affecting our horizontal movement. It's going to be moving us to the left 1. And then the -2 is outside the exponential function, and that's affecting all of our y values, so that's going to shift us vertically down 1 space. And the parent function that we're talking about is y equals 3 to the x power. So check on that, see if you were right. For the next one, I see a negative in the front of our function. So remember that a negative in the front of our function is going to change all of our outputs of our parent function to their opposites. So that's going to cause us to have a reflection over the x-axis. And then inside this function, right next to x, we have that -3. So it's going to be affecting all of our x values, and it's actually going to shift us to the right 3 spaces. And our parent function for all of this is log base 2 of x. All right, let's look at the next one here. I have another negative in the front of my function, so that's going to do that same reflection over the x-axis. And then I have a +1. Now just be really careful here. That +1 is not in the exponent. And since it's not in the exponent, then we're going to know that it affects us after we evaluate that e to the x function. So if it's happening after, it's affecting our output. So it's going to be shifting all of our y values up 1 space. And our parent function here is our e to the x, our natural exponential function. And for this last one here, we have both a 2 and a 3 affecting our function. And that plus 2, again, it's inside, is going to be moving us to the left 2 spaces. And the plus 3 outside is going to be shifting us up 3 spaces, where our parent function is y equals the natural log of x. All right, so now that we see all of our transformations, what we're going to want to do is graph each of those parent functions, just like we did before. So our parent function for the first one, coming back up here, the table, well, we know what the function kind of looks like, but it's nice to do a little table. I always do a table for our exponential functions just to get some nice, pretty numbers for the structure. So 3 to the first power is 3, 3 to the 0 power is 1, and 3 to the negative 1, remember that does the reciprocal, so we're at 1/3. So just for the parent function, right now, I'm going to draw that as a dotted line. At 1, I'm up at 3, 0, I'm at 1, and at negative 1, I'm at 1/3. So again, just drawing that in there, dotted, so I know what I'm transforming. Now it has a horizontal asymptote on the x-axis, so I'm going to think about moving that. It really helps guide my graph, so I really like to move that first. So if we think about our function is moving to the left 1, then that's not going to change the horizontal asymptote, but moving down 1, we'll take that whole horizontal asymptote and shift it down 1, so it's now going to be, instead of y equals 0, it'll be y equals negative 1. So then each of my points that I have, in particular 0, 1, because that's on every exponential function, think about where that will be. It'll move to the left 1 space and then down 1 space, which puts you right here. And I need to erase that red that I just made on there. Okay, and so that's that 0, 1 point moved, and all my points are going to move. So let's also take 1, 3. That's going to move to the left 1 space and down 1. So even with just those 2, I have a great idea of what my graph is looking like. It's the same shape, not stretched or anything, just shifted to the left 1 and down 1. So there's my graph, that red one. So that's y equals 3 to the x plus 1 minus 2. Now the domain for our exponential functions are always going to be -infinity to infinity, because you can plug in anything for our exponents. But the thing that will change is our range. So normally it's from 0 to infinity, but because I shifted down 1, it'll be -1 to infinity now. Okay, we're going to take a look at the next graph here. Now, our parent function for this guy is log, and for some reason, a lot of people aren't that comfortable with log, but if I ask you to think about its inverse, for some reason, we get a little more comfortable when we talk about y equals 2 to the x. So what I'm going to do, instead of starting with making a table for log, I'm going to make a little table for this exponential function, and it'll be really similar to what we just did. So I'm going to plug in a 1, I'll get a 2, 0, I'll get a 1, -1, I'm going to get a half. Now this is not the table I'm going to graph, it's the inverse. So for my parent function, it's going to have all my x and y's flip-flopped because it was the inverse. So I'm going to have a 2 getting me 1, 1 getting me 0, 1/2 getting me -1. And there's lots of other ways to graph it, but for some reason I find that students really feel okay about making that table, so it's really nice just to interchange all my x and y's for my log. So I'm going to plot those. 2 gets me up at 1, and 1 gets me at 0, and 1/2 gets me at -1. So it looks like what you would expect from a log graph. Now this is the parent function, so I'm just going to make it dotted. So that way we know the function that we want to move around. And again, it has a vertical asymptote now on the y-axis. So we need to do a reflection and we need to move it to the right. So I think about the reflection, maybe we can do this in 2 steps. So I'm going to draw the reflected graph, which means that if I'm at a +1 up here, I now need to be at -1. 0 still at 0, -1 is now at +1. So what I have here, I'm going to draw it still dotted, just kind of doing it in 2 steps. And so this is going to be negative that log graph. So that's the reflection. And the green one is the actual parent function, log base 2 of x. So finally, I need to do the shift to the right 3, which makes my vertical asymptote now at x equals 3. So I'm going to write that down here, x equals 3. And all of the blue graph, which was my reflected graph, is going to move to the right 3 spaces. So this is going to be now 1, 2, 3, 1, 2, 3, and 1, 2, 3, getting closer. So it should look just like the blue graph, but shifted to the right 3 spaces. So what I just did, this is my final, it kind of took me 3 steps. This is negative log base 2 of x minus 3. And so you can kind of see, we talked about that the inputs for your log always have to be positive, so we need to plug in numbers that are 3 or bigger, which makes sense for our graph. And so our domain will be everything to the right of 3, so from 3 to infinity, and our range for this guy, negative infinity to infinity. Okay, we're going to move on to another exponential function. And so again, this is like looking at basically like 2 to the x, but we have the number e there. So e is about 2.7, and we just did this on the previous page, but I'm going to still make a little table. So this is an exponential function. It's really nice to plug in 1, 0, negative 1. So we already know e to the 1, that's the 2.7. E to the 0 is 1, and e to the negative 1 is about 0.37. Okay, so we're going to sketch this one, exponential function, just the parent function, e to the x, 1 to about 2.7, 0 gets me 1, and negative 1 is about 0.37. So we already know exponential functions have this structure to them, and they have a horizontal asymptote. So we want to do all of our shifting. So again, there's a reflection going on in here and a vertical shift. So I am going to do this again in 2 steps, just like the last problem. So just to do that reflection over the x-axis, takes all of our y values and makes them opposite. So instead of 2.7, it's going to be at negative 2.7. 1 will be at negative 1, and 0.37 will be at negative 0.37. So again, just kind of dotted. This is the reflected exponential function. So this is the negative e to the x. This one was e to the x. So then we still have to shift up 1. So we're going to take this blue graph that we just made and shift it up 1, which makes the horizontal asymptote now be at y equals 1. And all our points will just shift up 1 space. So instead of being at 0, negative 1, it'll be at 0, 0. At 2.7 is now at 1.7. And this 0.37 will be close to there. So just a sketch. But this is going to be the function reflected and shifted up 1. So the red one right here, this is negative e to the x plus 1. And since it's an exponential function, when we're talking about the domain, it's still going to be negative infinity to infinity. Nothing changed with that. But because we did that reflection and shift up, our range now will go from negative infinity, that's the lowest it goes, all the way up to 1, not including 1. All right, and so this last one here, we're back to a log function. So since log is the inverse of our e to the x, again, it's really nice if we just kind of think about the e to the x, which we just did up here, and we can make a table for the natural log by interchanging those x and y. So 2.7 gets you about 1, 1 gets you 0, and 0.37 gets you negative 1. So our parent function will be at that 2.7 up at 1, 1, 0, 0.37, negative 1. It has a vertical asymptote at x equals 0. And so again, here is our parent function, and that's our log, our natural log. So we need to shift it to the left 2 and up 3. So I'm going to do this all in one step. And the first thing I like to do is move my vertical asymptote. So left 2, up 3 would just really move it left 2. And then I'm going to take my main nice point here. I really like moving the 1, 0. So if I move it to the left 2 spaces, 1, 2, and then up 3, 1, 2, 3, I basically know that's where my log function is going to be hanging out. So you can just draw a quick sketch if you like, or you can try and move another point if you want to as well. So I'll move that guy. If I move it to the left 2, 1, 2, and then up 1, 2, 3. You can see the growth that way. And I'll just sketch out the graph here. So we know the vertical asymptote is now at -2, and we have our domain then would be from -2 all the way to infinity. And our range for all these log functions is -infinity to infinity. And so one thing that people notice is that if you're trying to graph an exponential function that's been transformed, so if you look at the first guy and the third guy here, the horizontal asymptote is affected by the movement down. And I just realized that this graph, we need to fix it. Oh, we already need to fix it. So I said down 1, but there's a 2 right here. So this should actually be down 2 spaces. Sorry about that. Oh, let's fix this. So the whole graph here, when we move down 2, let's see if we can do some erasing. So we should actually have a couple changes here. So it's going to change our asymptote and it's going to change our range. Okay, so if we're going to move down 2, that's going to be at the horizontal asymptote at -2. Sorry about that. Let's see. And so the range will be from -2 to infinity. So you're just a little short on that. But our point social can do the same thing. We're going to move left 1 and then down 2 spaces, left 1 and then down 2 spaces. So it'll look really similar, just I was off by 1 space moving downward. So this is the graph y equals 3 to the x plus 1 minus 2. But what I saw with that error and what I was trying to point out was that when you look at these exponential functions, that movement, that up and down movement, it's what's changing your asymptotes. And when you look at the exponential functions, I mean the logarithmic functions like the second guy and the third guy, it's all about that left and right movement. So to the right 3, that made our asymptote, and this x plus 2, that made our asymptote -2. So you can see how that shifting affects the asymptotes.